everyone. In this video, today we are going to see how to solve the buy and sell stock problem. The problem statement says that you are given a list of stock prices for a given particular stock, and the stock prices may represent the prices of the stock for each day. So in this problem statement, what you are asked to do is basically find the maximum profit that you could have made by buying and selling the stock. So assume that it's a single stock, and you need to like buy the stock and then sell the stocks. So there are multiple variations of the same problem. So in one of the variations that you will find is that you are only allowed to buy the and sell the stock once, basically do a single transaction. In another variant, you are allowed to do as many transactions as possible. Similarly, in another variation, it adds a like new constraint that for each transaction that you make, for example, like you buy and then when you are selling the stock, you have to pay a transaction fee of some amount X. And then there is another constraint of similar problem is that there is a cool down period. So basically, when you are selling the stock and you are not allowed to buy the stock again on the next day. So you can only buy the stock after at least one day after. So that is another variation. And then there is another in another variation, you are allowed to do at most k transactions. That is, you are allowed to only buy and sell at most k number of times. So these are the possible variations that you can find for the same problem over the internet, on various programming contest websites, lead code, coding contests, etc. So today in this video, we are going to show a more generic approach to solving these problems with all the different constraints in place. And we are going to use a kind of like a dynamic programming approach. So let's take the first variation. So the first variation is shows that it asks you to find the basically maximum profit that you can make by buying and selling the stock only once. So let's say you have kind of this stock prices. Just to say, let's say 8, 3, 7, 2, 1, 6, 3, 9. Okay, let's say I have this stock prices for the last 8 days. I want to find the maximum profit that I can make by buying and selling the stock only once within this time frame. So as you can see, the maximum profit that I can make is 8 units. Why? Because if I buy at 1 and sell at 9, then I'm making the maximum profit of 8. So this is how I'm going to make the maximum profit. But how do you go about and solve this problem? So one of the approaches, easiest approach that you can think of is, for each day I find the day from 0 to I minus 1, which has the minimum price among 0 to I minus 1, and take that day as the buying price, and the selling price is the day of I. So for example, if I take my day of I as 7 here, then from 0 to I minus 1, which is in this region, my stock price, minimum stock price is 3. So if I'm going to sell the stock on uh, day third day at 7, then I should buy at 3 to make the maximum profit by selling the stock at 7 units. So I make a profit of 4. Similarly, if I'm selling the stock on this day at price 6, in that case I should buy my stock at 1, because from day 0 to 5, 0, 1, 2, 3, 4, yeah, 0 to 4, my minimum stock price is 1, and I should buy at 1 to sell it at 6 to make the maximum profit. In this way, you can see that for day last day, which is stock price is 9, I should buy at 1 again to make the maximum profit, which is 8. So this is one approach by which you can solve this problem. Now let's look at a more generic approach. Let's erase the screen first and see. Then, okay, okay, my screen is clean now. Okay, so now let's imagine the daily activity. Basically, I'm each day I am either like buying the stock, or I'm selling the stock, or I'm let's say doing nothing. So basically, each if I model my activities on a tree, so on each day I can have three different possibilities, which are like I buy the stock on that day, I sell the stock on that day, or I do nothing on that day. So if I draw a tree kind of a structure, so this is my like let's say the root node, and let's say for the day one I can have three options: buy, sell, or I can do nothing. Let's say I do nothing, I can say it's like it's pass p, I can say it's p. Okay, similarly for day two I can have again like three different options for each possibility from level one: buy, sell, and pass. And here also I have buy, sell, pass. Similarly, buy, sell, and pass. So as you can see, like this tree can go down to n levels, where n represents the number of days for which I want to maximize my profit. So now, given this tree data structure, how do I find the maximum profit that I can make? So one possible way that you can imagine is that if you take a path among this tree, let's say buy, then sell, then do nothing, and so on, like till the nth level. If I take any one of these paths and I calculate the maximum profit I have made along that path, and then I consider all the possible paths in this tree, then I can find out the maximum profit that I could have made by buying and selling the stock on from day 0 to n minus 1. So basically you are like evaluating all possible paths in this tree to find the maximum profit that you can make. Okay, so now what if I tell you that you do not need to evaluate all possible paths in this tree, but as you know that you can use memoization technique to solve this problem much more efficiently using dynamic programming. Okay, so before going into dynamic programming, let me ask you this: like, if you do like evaluation of all the paths in this tree from day 0 to n minus 1, that is you have n levels, and each level has three different possibilities. So what is the time complexity in evaluating all these paths? So if you do a like a simple mathematical calculation, then you can see that for each level you have three possibilities, right? And then what is the like total number of paths that you have to evaluate so you can see that at the last level, how many nodes, how many nodes would be there, leaf nodes basically, at the last level. So at level 1 you have 3, at level 2 you have 3 square, at level 3 you have 3 cube, at level n you would have 3 to the power of n nodes, right? So this would be my time complexity, basically to evaluate all different paths, because the number of leaf nodes is equivalent to the number of possible paths in this tree, correct? So my time complexity is O of 3 to the power n, which is, as you can see, it's exponential. So I should not go into that route. So let's now try to see a much more efficient strategy using dynamic programming. Okay, just let me clear this. Okay, okay. So in this approach, let us represent a variable dp. Okay, this is a variable. It's a 2D array, and okay, I have two indices. Okay, so in the first, I would this for this index there are two possibilities. Let's say buy and sell, uh, B and S, let's say. And in this index I have 0 to n minus 1. So what does, let's say now, I can say dp by I. So what does this value represents? Question is, what is the value this value represents? So now this value represents the maximum profit that I could have made from day 0 to day I, uh, where my last activity was a buy activity. So this position denotes what is my last activity. So if my last activity was buy, so I will put B here. If my last activity was sell, I will put S here. Correct. And what is the maximum profit I could have made by doing my last activity as a buy activity from day 0 to I. So to make it a much more clearer, you need not have to do a buy activity on the ith day for this quantity, to find this quantity. Why? Because this says only the last activity was a buy activity from day 0 to I. So I could have done the buy activity on, if let's say I was, let's say, 10. I could have done the last buy activity on day, let's say, 6. And I did not do any activity from day 7 to day 10. Or I did last activity was, so I would, for this quantity I would take the value evaluated on day 6, which is dp of yeah, b of I, from for I equal to 10. So similarly, I define dp of s I to be the quantity maximum profit that I could have made from day 0 to day I, where my last activity was a sell activity. So this is similar to this one, but here I have my last activity as a sell activity. So now let us okay, so why I am just putting like two variables like b and s. So as I mentioned earlier, that we have three possibilities, right? We also have a possibility of passing. So as you can see that how I'm defining this variable. So in this definition, I'm saying the last activity was either a buy or a sell. So even if you, let's say, do nothing, so then also my last activity would be buy or sell, depending on what was my last activity before passing on for that day. So I only have two activities to evaluate on. So pass is not an activity, it's just that I am ignoring that variable. So now let's jump to how we are going to compute these two quantities. Okay, as you know, like in any dynamic programming approach, we need to define certain recurrence relation or relation to say to evaluate basically the variables using memoization. And we also need to have some kind of edge case to basically the condition where, let's say, I equals to 0 or I equals to n minus 1, all these base case conditions. So now, like, let's try to evaluate how we are going to formulate the recurrence relation for this two variables. Okay, let's start with the dp of b of I. Just clear it a bit so that it is easy to follow. Okay. Okay, now let's see how we are going to compute dp b of I. Okay, so as I said earlier, so dpb of I is the maximum profit from day 0 to I minus I, where my last activity was a buy. So for to make this variable the maximum from day 0 to I need to also evaluate a max over dp, basically the all the days prior to I, so I minus 1. So I need to also evaluate, basically compare the current profit with the profit maximum profit I have made till I minus 1, so that I can consider today's day to be maximum or not maximum. And then for today's day, let's say day of I. So what is the profit that I can make on day of I? So if you see, like if you for the ith level in this tree, if you draw a node with b here, so you can have like three different possibilities how this is connected from the previous day, right? You can have a previous day as a buy or a sell or do nothing, let's say pass, correct? So, according to the first problem statement, where it says that I am allowed to only buy and sell the stock once. That means I am not allowed to do like sell and then buy again. So this is not possible because that means I'm doing like two transactions. Like I'm first selling it once, buying, selling once, and then I'm buying again. So that's basically a two transaction. Also remember that according to this problem statement, I'm not allowed to sell before doing buying. Like basically, I cannot sell without owning the stock. What that implies. Similarly, if my previous day was a buy, I cannot do a buy next day. Why? Because then, according to the statement, that I cannot basically buy without selling the stock. I have to first sell the stock. If I'm buying on day I minus one, I should sell the stock. Then only can I can buy. Similarly, yeah, now it only thing remains is pass. So basically it says that if I'm doing the buy on day i I cannot have done any operation till 0 to I minus 1, and my this is my first buy activity. So if this is my first buy activity, then my total profit that I am seeing is a minus of, let's say, prices of I. So if my prices array is in my list of prices, that stock prices that is given to me as input is prices. So my profit that I'm making by buying on that day is minus of prices I. Why minus of prices I? Because so if you think like it's much more intuitive to associate a buy sorry a profit with a sell activity. Like when we are doing a sell operation, it we are associating a profit or a loss, but generally it's very counterintuitive to associate profit or loss with buy activity, because when we are buying, we are obviously making a loss because we are spending money to buy that stock. So so my profit actually reduces by this amount minus prices of I, and that's why my profit has a negative sign before this. Make sense? Okay. Now let's move on to how we are going to compute DPS of I. Let's clear this a bit. Okay. Okay. Let's see how we are going to compute that. DPS of I. Okay, so how we are going to compute? Okay, now as before, since it's a maximum, so I should take max over dp s of I minus 1. That's the maximum profit by doing sell last activity as a sell activity till I minus 1 at take. And then I need to consider the possibility of doing a sell activity on the ith day. So what is the maximum profit that I can make if I do a sell activity on ith day? So as before, let's say I have this cell S node on the ith level. It has three different possibilities by which it is connected to I minus 1th level, like buy, sell, or pass. Okay. Now, according to the problem statement, uh, this path is invalid, where I'm doing sell on I minus 1th day and then I'm doing sell on ith day. So this path is invalid by our earlier reasoning. The only also I am like so if you like if you remove this like p from here, let's say my possibilities like depending on what activity I do. So if you remove the pass also, like why this pass is not valid, I would explain it later. Because like you so one of the constraint is that you have to sell the stock before sell the stock first by first buying the stock. You cannot sell without buying the stock. So if you consider, if you like take all the basically pass, like if you do not have not done any transactions so far before doing this sell operation, that is an invalid approach because you have to first do a buy activity. So my only possibility that remains is that I have done a buy activity last, like from day 0 to I minus 1, and then I'm doing a sell activity on the ith day. So my maximum profit would be like dp by till I minus 1th day plus of prices of I. Why this is so? Because when I'm selling the stock on the ith day, I am it implicitly assumes that I have already bought the stocks on some previous day. So it could be the I minus one a day, or it could be the let's say first day or second day, any day. But it was the last activity last buy activity, and after that buy activity, this is the next activity, which is sell. So it implies that my last activity, the maximum profit that I have made by doing a buy activity last until I minus one a day, and my current price is prices of I'm selling it this price. So my profit is this plus of this. So if you take this compute this quantity, then you can now compute dp of s of I for all I from 0 to n minus 1. So this is how we are going to approach this problem in a more generic sense. Although this approach seems a bit like twisted as compared to the earlier approach, where we were like for each day I, we are considering the minimum value from day 0 to I minus 1 as the buy price, and selling an day I at prices of I. This approach is a bit like complicated to someone not very comfortable with, let's say, dynamic programming or trees. But you will see later that this approach is much more extensible to the other variations of the problem that we discussed earlier. So now we'll look into the next variation of this problem, which is you are allowed to trade this stock any number of times. It's not only a single time, but you can trade the stock any number of times. Okay, now let's see what are the possible approach first. Okay, so let's do a clear of this script. Okay. Mm, okay. Okay, now let's take the previous example itself, where my prices was, let's say, 8, 3, 7, 2, 1, sorry, 6, 3, 9. The same example, let us take this one. Okay, so what is the maximum profit that you can make by trading the stock any number of times? Okay, so let us propose a hypothesis. The hypothesis says that uh, buy whenever the stock price is decreasing, and sell whenever the stock price is maximum. So it's in simple terminologies, like buy when it is low and sell when it is like high. It's in like simple trading terms, correct? So in this example, so what are the different points where I'm buying and selling? So if you see, like when I'm at stock price 3, my stock price is decreasing, so I should buy here. I do a buy here. Okay, and then it goes to 7, which is high, because after 7 we have 2, so it is again decreasing, so I should sell at 7. Similarly, after 7, since we are the stock price is decreasing, do a buy again here, correct? uh, yeah. So now the next day you can see that the stock price is still decreasing. So I should what I should do is I should sell the stock on the same day as 2, and do a buy again on this on day where the price is 1. uh, Now on the next day you can see that the stock price is 6, which is high than 1. And then so uh, I should sell the stock, because after day on this day again the stock price is decreasing, so I should immediately sell on day where the stock price is 6. Similarly, if I am, then I go to buy on this day where stock price is 3 because the stock price decreasing, and then again I sell on the day where it is increasing. So my sell is this. Okay, so if you like if you kind of like draw a chart, stock chart, to say, so you have somewhere 8 is this point, then you have 3, then you have 7, then you have 2, then you have 1, then you have 6, then you have again 3, then you have 9. Okay, so if you draw this chart here, okay, now you can basically you buy at points where it is it's basically this kind of regions where you are buying the stock. So you buy here, then you buy here, then you buy here, then you buy here. Okay, where are you selling? You are selling wherever you have basically this kind of shape. So you are selling it here, selling it here, in this region where you brought at, let's say, you so here the stock price is 2, correct? So in this case, you can see that it's neither this shape or this shape. So your basically stock price is decreasing from this day to this day. So if it is so, so you buy the stock and sell the stock on the same day itself, correct? According to the problem statement, you are allowed to sell the stock on the same day as you are buying. So you should like sell the stock on the day you are buying if the stock price is decreasing on the again on the next day. So this is one approach. You can. This is one hypothesis that I'm proposing that should work for solving this problem. So what is the maximum profit that you can make here? Let's say profit. So for these 2 days, it's like 4. Okay. Here I'm buying and selling on the same day, so it's 0. Here I'm making a profit of 5. Similarly, here I'm making a profit of 6. Okay, so my profit is 15 units. As you can see, if I'm allowed to do like multiple transactions over the time frame, my total profit is more than if I'm allowed to do only a single transaction, which makes sense because there are like lots of opportunities that where you can buy and sell this stock. Okay, now before showing the how to solve this problem using the dynamic programming approach, let us convince ourselves that this approach or the hypothesis that I suggested just now makes sense, and it should hold true. Basically, I'll give a simple. So in this proof, so how we'll approach this? Let's see. Let's clear the screen first before showing how the proof works. Okay, now let's see. So my hypothesis was that you buy the stock when the stock price has like decreased from the previous day, and you are selling the stock on that day where the stock price is high, and on the next day it is again decreasing. So basically, it says that, let's say I have some stock prices, let's say x1, x2, x3, till let's say xn. Okay, so now let's say I have, let's say let's consider till x5, for example. Let's consider this x up to x4. Okay, or let's not denote with x. Let's denote with a, b, c, d. That would make it is much more easier to understand. Okay, so let's say I have this stock prices for 4 days: A, B, C, and D. Okay, for this 4 day. Now I'm saying that, let's say A, this is the given that A is less than B, C is less than D, and B is greater than C. So basically it says that like A A is here, B is here, C could be somewhere here, and D is somewhere here. Okay, A, B, C, D. Okay, now you can see the possibilities. There could be like endless, like multiple other possibilities. Not this, not the, this is this could this is not the only possibility. It could be that D was, instead of here, D could be somewhere around here, correct? Let's say D, this is, let's I call it D prime. Okay. Or C, instead of C being here, C could have been here. Let's say C prime. So these are the different possibilities that where C and D could like, but the relations that that we define, that A is less than B, B is greater than C, and C is less than D. So these three relations holds true always. Only thing is that the relation from like how how big B and C, is relative to C, or how big B is relative to A, all these are not defined according to this problem. But let's try to figure out whether if I do the let's say buying and selling according to the hypothesis, will I maximize my profit? Okay. So let's say in this case, my profit would be like I'm buying at A, I'm selling at B, which is B minus A, and again I'm buying at C and selling at D, which is D minus C. Correct. So my profit is B minus A plus D minus C. So this is my current profit according to my hypothesis. Okay. Now see, now let's imagine that instead of let's say instead of selling at selling the stock at B, I sell the stock at D. So I do not do a sell transaction here. I buy at A and I sell at D. So let's say I am here, and my D is somewhere here, around here. So I can obviously make a profit if I buy at here and sell at D prime here, correct? Because D prime is higher than A according to this figure. So there is no one to say that this no way to say whether D prime is higher on should not, we should not sell at D prime. Okay. So let's see what is my profit there. So in that case, my profit would be, let's say, D minus A. If I am buying at A and selling at D, my profit is D minus A. Correct. So now let's try to prove whether whether my profit, this profit is higher, or D minus A, this profit is higher. So how do I show that which one is higher? Let's do a subtraction. Okay. So just okay. Let's do a subtraction. So I subtract the first profit, sorry, I subtract the second profit from the first profit. So in that case, what would be my value? So B minus A plus D minus C minus of D, and minus of A would be plus of A. So this would be my difference of the two profits, correct? So as you can see, the D's cancel each other, A's cancel each other. So I am remaining with only B minus C, correct? Now, according to the definition of the problem, I mentioned that B is greater than C, which implies that this quantity is a positive quantity, correct? So it implies that if I use the strategy where I buy at B A and sell at B, and then buy at C again and sell at D, the profit I am making is higher than the profit I could have made by buying at A and selling at D. So this kind of shows that this hypothesis should hold true. Okay, now let's try to put this problem into the dynamic programming approach that we saw earlier. Let's erase this a bit. So according to our earlier DP approach that we saw, we have two variables, DP B of I, BI, and DP SI. So we have these two quantities that we need to compute. So now in this, for this problem, how we are going to compute DP B of I? Okay, so as before, we would have again a max over dp p of I minus 1, because it's a maximum. And for the profit that I'm going to make by buying on day of I. So remember that in the earlier problem, we were not allowed to do any activity before doing a buy activity, Correct. So we had this minus prices of I earlier, right? If you remember correctly, we had we had minus of prices I for the second term in this relation. But in this problem, uh, you are allowed to do as many transactions as possible. So you are allowed to do a buy transaction or as well as a sell transaction in this problem. So if you but remember, okay, according to this problem statement, you are not allowed to like again like sell or buy before selling the stock. So you are only allowed to do a sell operation before this buy. So my profit for day of I would be day of dp of s of I minus 1 plus dp of sorry, not dp, dts of I minus 1 plus, sorry, minus prices of I. So this is my profit. That this is my maximum profit with dp of I that I can make. Note that this term is additional, which was not present in the earlier problem because we were not allowed to do a sell activity before doing a buy activity in the previous problem. But in this problem, we are allowed to do that. For dpas of I, it should be the same as before. Why? Because we are already taking into account the buying activity. So in this case, my relation would be same dp I minus 1 comma dp of I minus 1 plus prices of I. So this is same condition as before. So now if you solve these two relations using memoization, dynamic programming, you are going to land up at the same solution that we showed with the other approach. Okay. So now this completes the second variation of this problem. Now let's move on to another variation of the same problem. The other variation which asks us to, let's say, have a cool down period. Okay, what's a cool down period? So according to this problem statement, you are not allowed to buy the stock the next day after selling the stock. So if I'm, let's say, if I'm doing a sell activity on let's say day 5, I cannot do a buy activity on day 6. So this is not allowed. I can do a buy activity from day 7 onwards. Day 7 onwards. Correct. So this is the other variation. So if you add this constraint to this relation, the recurrence relation, how does this recurrence relation modifies itself? So if you see, yeah, just place this. If you see this recurrence relation for the first dpb of I, you can see that my dpb of I uses this value dps of I minus 1. So it says that the cell activity I have done till day I minus 1. So I only need to update this value and make it dpi minus 2. Why? Because if I'm doing a cell activity on day of I minus 1, and this value takes the cell activity for day I minus 1 into account, then I would get a wrong answer because I am not allowed to sell on I minus 1 and do a buy again on I. So I should have till day I minus 2. So dps of I minus 2 minus prices of I. So this is the only change that is required to handle this other constraint where I have a cool down period of 1 day at least. If you have a cool down period of, let's say, d days, so it's just like you have to update this to I minus d value. So in that case, instead of I minus 2, I would have like I minus of d, I minus d days before. So that is the only change that requires to be done. Okay, now let's move on to other constraint of where we have a transaction fee associated with each cell activity. Okay, so let's say that I have a transaction fee of, let's say, some x transaction fee. Transaction. I'll just write it up. Transaction equal to x. This is the transaction fee associated with each cell activity. So in that case, how do I update this relations? You see that I just need to update dps of I, this relation with by adding a minus of x here. So my profit, maximum profit that I'm going to make on this day is this one, dps of dpb of I minus 1 plus prices of I minus of x. So this is the only change that is required to handle this problem, this change. I mean, like, you have a transaction fee associated with each cell activity. Correct. So now you can see that using just two variables, I am handling all the different possible constraints. So if you do not use this approach, then you will have to basically have a different approach for each of these constraints and handle the problem differently by adding different variables and conditions, etc. But with this dynamic programming approach, you are just updating this recurrence relation with minimal number of changes. Next, what I'm going to show is how we can modify this recurrence relation to handle the case where we are allowed to do only or at most k number of transactions. So k can be like anything from like 0 to n minus 1, and I can do at most k transactions and have to find the maximum profit that we can make out of that. Let me clear the screen first. Okay, it's almost clear. So now, uh, what my problem statement asks is I can do at most k transactions. So now, what I do is I update the dynamic programming variables and add a third index. So I earlier had this dpb of I, correct. So which was like the maximum profit till day I, when the last activity was a buy activity. Now I add another variable here. Let's say j. Okay, and j will range from 0 to k, where k is the maximum transactions that I'm allowed to do. So then what this quantity indicates? It indicates that the maximum profit that I can make from till day of I by doing at most j transactions when my last activity was a buy activity. So this this one this value was from coming from the previous iterations. This is remaining same. I'm just adding this another index j, which says that the maximum profit is at most from j transactions. Similarly, for cell also I define, I add another index j here, which says that the maximum profit I can make from till day of I by doing a cell activity when my last activity was a cell activity, by making at most j transactions. At most j transaction. Keep in mind that word at most. So it can be like less than j transactions. So if j is, let's say, 5, so my maximum profit can come by doing only 3 transactions. So I do not need to do 5 transactions. So we should keep that at most word in mind while doing the recurrence relations. Okay, now let's try to figure out how to compute this two quantities, updated quantities, by our recurrence relations. Okay, so just so I'll define the recurrence relation for by activity first. Okay, so note that It is like the same, similar as before, but I have max of dp of b of I minus 1. Okay. Okay, so I one thing is that now I have to use loop over dp using two variables, both I and j. Correct, because I am let's say looping over I from 0 to n minus 1, and I have another for loop inside j, but looping from let's say 0 to k. Correct. Now, then using this two for loops, I'm computing these relations inside this for I and then for j. So it's dp of here b I j. It should be computed here. Correct. So my dp of I, sorry, I'm bi of j. How this we can compute this is basically it's we can find the maximum over uh, j. Okay. So since it's the jth transaction, so currently maximum transactions is j, so my max is over dpb I minus 1 j. Transaction is the remaining same, and we are computing over uh, uh, I ith index, so dp I j, and then we add the other term, which is dp cell I minus 1 j minus 1 minus of prices I, just to make it a bit clearer. Yeah. So what this is does is what it does is it computes this dp, uses dps of I minus 1 j minus 1 and subtract minus of prices I. Earlier we were not adding this index dimension to the problem. We are computing only dps of I minus 1, and now we are adding j minus 1. Why specifically j minus 1? Because remember that when we are doing a buy activity on the ith day, it is counted as a new transaction. So that means, like, if my buy activity creates basically it starts the jth transaction, then the prior sell activity from which I am following up for this buying activity, so that should end at j minus 1th transaction. So this is a new transaction. That's why I am having j minus 1 with the sell activity from the previous transaction, and also like till day I minus 1, which is same as before. So that is why we are having j minus 1. Similarly for dps I of j, here I just have to like add it similarly, dp s I minus 1 j, same as before, and then the next term is dp b of I minus 1 j. Note that here I'm adding j, not j minus 1, plus prices of I. Sorry. Okay, so why I'm having j here instead of j minus 1 from the by variable? Because when I'm doing a sell activity, it after doing a buy activity prior to the sell activity, this is considered to be the same transaction. So earlier, when I'm doing a buy activity after sell activity, the buy activity becomes a new transaction. That's why we are considering till j minus 1. But here, the buy activity is part of the j transaction only. That's why, excuse me, we have j and not j minus 1. So since, as I mentioned, that this variable, it considers all the maximum profits till transactions 0 to j. So I do not have to basically consider all the values of j from, let's say, 0 to k for each value of j. So it automatically includes those calculations within this within itself. So as you can see, like, this is the only modification, these are the only modifications that is required to handle this constraint, where I am allowed to do only or at most k transactions. So yeah, that concludes my explanation or the theory behind, like, how to use dynamic programming to solve buy and selling stock problems. In the next video, I'll show how to implement one of these problems. Basically, let's say this constraint where I can do at most k transactions with the Python code. Till then, stay tuned.